Okay, so here we're going to talk about organic pollutants, things like hydrocarbons, polychlorinated biphenyls. You probably heard the term PCB before, um, and insecticides, herbicides, pharmaceuticals, personal care products. There's a lot of organic pollutants out there, so these are just some of them. Okay, so what does organic mean? Maybe you remember this from chemistry. It essentially means that they contain carbon and hydrogen, so molecules that have both of these things. There's a possible exception of methane. Some people do not consider that to be an organic compound. I'm not going to try to trick you with that at any point. I just want you to know that that is out there. So here's your first test of that concept. Which of these molecules do you think are considered organic? So there may be more than one answer. You can pause and think about that. Stop the video maybe. And the answer here is B and D. So glucose and benzene, they both have carbon and hydrogen. So they can have other things. There could be oxygen, there could be nitrogen, there could be sulfur, phosphorus, pretty much anything. But there has to be carbon and hydrogen for it to be an organic molecule. Okay, so we've got our first class of compounds are hydrocarbons, and these are carbon and hydrogen only compounds, more or less. So hydrocarbons usually only have carbon and hydrogen. They're nonpolar, not very reactive, so that means they don't react with other chemicals in the environment very, very easily. But there are other compounds. So these are compounds with oxygen functional groups that are more polar. For example, OH here makes things into an alcohol, and CHO and O2. They're more soluble and more reactive, and you may kind of think back to your chemistry, you know that these oxygen molecules can make things more polar, right? Because they often have lone pairs, or they're more electronegative. So they tend to be a little more reactive and more soluble in the environment. Okay, so hydrocarbons are kind of the first group that we're going to talk about. They have only carbon, only nitrogen, more or less. Sometimes there are impurities of nitrogen and things like that involved in them. But by and large, the bulk of any hydrocarbon is made up of carbon and nitrogen. Okay, so its properties are sort of determined by how many carbon atoms are in the molecule. Or another way to think about this is how heavy are they? What is their molecular weight? And this determines what phase that they'll be in. And by phase, I mean a gas, liquid, or solid at a normal temperature and a normal pressure. So low molecular weight hydrocarbons, that means there are less than 4 carbons usually, like to be gases. Intermediate molecular weight, that's about 5 to 17 carbons. They like to be liquids at normal temperatures and pressures. And very high molecular weight, usually more than about 17 carbon atoms in the compound, they like to be solids. Okay, so here is propane. This may be a give me to some of you guys. At normal temperature and pressure, propane should be a gas or a liquid or a solid. So you can think about that. There are 3 carbon atoms there. It should be a gas, right? There are only 3 carbons, so it's a low molecular weight compound. It wants to be a gas at normal temperatures and pressures. We also use it to heat our homes to some degree, and run camp stoves, and barbecue, so you might already sort of be familiar with propane. Okay, there's a little bit more on what kinds of hydrocarbons are out there. There are saturated alkanes, so this means that there are only single bonds, lots of hydrogens all around every carbon atom. So they're stable and unreactive. Then there are unsaturated alkenes and alkynes. This means that there are double or triple bonds, and they're more chemically reactive than alkanes. But they still follow that same rule about the number of the number of carbon atoms and what that means for whether they want to be a gas, a liquid. So here we've got 5. These all want to be liquids, less than, or 4 or less. All of these molecules are gases, regardless of the number of bonds. So the G here is gas, the L here is liquid. You remember, 17 or more carbons, you generally have a solid. Okay, so here are the gases, and here are the liquids with 5 or more carbon atoms, up to 17 about. Okay, we also have aromatic hydrocarbons. So this is when you have a ring of carbons, like a benzene ring over here, simplified diagram with carbons at every corner here. Here's the molecular formula C6H6. So this is the smallest aromatic compound that you can have. This is benzene. So these tend to be liquids or solids, and so why not a gas? Because there's always more than 4 carbons, right? There's 6 carbons in the smallest aromatic compound. So you're going to have liquid like petroleum or benzene, and even solids like asphalt over here. Okay, so polycyclic aromatic hydrocarbons, often referred to by people like the EPA as PAHs. So these are 3 or more rings, and they can actually form mutagens, so not so good for people. And that's actually what asphalt is. It's a polyaromatic hydrocarbon. Polycyclic aromatic hydrocarbon. Okay, so then we're going to talk a little bit about polychlorinated biphenyls, PCBs. And these were used a lot in electrical transformers that you see up on electrical poles. So they're very stable, very unreactive, viscous liquids, 6 or more carbons because they're aromatic compounds. Low volatility and low water solubility. So what are they? They're things like hydraulic fluids, coolants, insulation fluids, and transformers. Plasticizers and paints, lubricants. This is because they're so stable and unreactive, and they form viscous liquids so they can be used to sort of lubricate things and keep things running the way that we want them to run. Okay, so they're from manufacturing. They come from manufacturing waste and careless disposal or dumping. And here's the bad news, right? We used them for all sorts of things before we knew sort of what the bad news was, and then we've since found out that they're carcinogens, endocrine disruptors, can be immunosuppressants, and have reproductive and developmental impacts. So we've since pulled way back on using PCBs. They used to be pretty much everywhere. And in fact, they've been banned in many countries, the US since 1979. Okay, so insecticides and herbicides is something we think a lot about here in Vermont with sort of the agriculture that goes on here. So there are a lot of different kinds of insecticides. I'm only going to talk about a few here, some of the more common ones. Organochlorine insecticides, these are stable solids. They're persistent, that means they're not easily broken down. And they have low vapor pressure, meaning they're not volatile, but not volatile. They're not going to turn into gases and float away. And low water solubility. So here are some examples. DDT, which we don't use right now in the US. It's an endocrine disruptor. It is used in other parts of the world because it's incredibly effective. Lindane, which is in use right here. You can see a lot of chlorine atoms like with the PCBs. It's a neurotoxin. Here's aldrin, again, a lot of chlorines, hence the organochlorine name, right? Highly toxic, has that LD50 of 40 to 60 milligrams per kilogram in rats. Okay, organophosphorus, so you can kind of see where this is going. It's organic compound with phosphorus, just like the organochlorine was an organic compound with chlorine. These are in wide usage. This is malathion. It's usually liquid, some solids out there. It's less persistent than organochlorines. It has low water solubility, but some volatility. Health impacts, it does have them. In fact, it was developed during World War II as a byproduct of nerve gas development, so makes sense. It's a neurotoxin. It's generally toxic, but organophosphorus insecticides have a wide LD50 range, anywhere from 1 to 1,300 milligrams per kilogram. And it has more chronic impacts. So if you are chronically exposed, you can end up with cardiac and even psychiatric impacts. Okay, and neonicotinoids, not going to talk too much about here, either because we will be doing a case study or have already done a case study on neonicotinoids, so you're going to learn a lot about that. Okay, the last thing I'm going to talk about are pharmaceuticals and personal care products, and there's not a whole lot of information out there about these things yet. People are very interested, though, in trying to figure out even what's in personal care products, so what is going into our water, and then pharmaceuticals have been found in surface waters. Mainly these things are coming from sewage outflows. Our treatment plants aren't equipped to deal with these sorts of things, so they just flow through the system. And then there's also the fate and transport of antibiotics used to treat farm animals and fish, even. What happens to all of those? Um, so again, we don't know that much about this. There's still low levels throughout the environment, and we don't know that much about the toxicity and sort of the larger impacts of these things. But there's a great number of them forming complex mixtures in the environment. We just really don't know what's going to happen with these things. So it's perhaps a little bit scary to think about, but also maybe really interesting to you. This is a field that people don't know that much about yet. So if it interests you, you should check it out. Okay, so that's the end of organic. We'll talk about radioactive isotopes, gases, and nanoparticles in class. So again, thanks for watching.